In this video, we are going to see about the mathematical induction. The principle of mathematical induction is, suppose if we have a statement, say P of n, and if we want to demonstrate that the statement P of n is true for every n where n is an integer, then we can prove that for the case when n is 0, n is 1, etc. and say P of k, but if k is large, then we cannot accomplish this completely. We have accomplished this very little if we are using this method of proving P of 0, P of 1, etc., P of k. So in order to get the proof for the principle of mathematical induction, maybe we can follow a different technique. In this, in order to show that for every n P of n holds, we can make use of two different properties here. We would like to check whether these properties are satisfied. The first one is the base case. That is, we have to check whether the initial condition holds good. Suppose if it starts from n equal to 0, we have to show that P of 0 is true. And we have to check the induction step. In this, we have got two different stages. One, we should assume an induction hypothesis. That is, we have to assume that the result P of k is true. Assuming that P of k is true, we have to show that P of k plus 1 holds. So in order to use the mathematical induction, we will be using these two steps. One, the base case, the other one, the induction step. Let us use an example to prove this result. Let us prove that this statement 1 times 1 factorial plus 2 times 2 factorial, etc., n times n factorial is n plus 1 factorial minus 1 for every n greater than or equal to 1. So if we want to prove this result, we have to take the given result as some P of n, and we know that the initial condition here is n is equal to 1. So let us assume that P of n is the given statement. 1 factorial plus 2 times 2 factorial, etc. is n plus 1 factorial minus 1. For the base case, we know that we have to prove that n is equal to, for n equal to 1, the result is true. The left-hand side of this equation is 1 times 1 factorial, which is 1. And the right-hand side is 1 plus 1 factorial minus 1, which is 2 factorial minus 1, equal to 1. These two are equal, and hence it is true. Then the second step, we have to find the inductive step, for which we need an induction hypothesis. That is, let us assume that the result P of k is true. By assuming P of k is true, we have to check the result P of k plus 1. The left-hand side of P of k plus 1 is 1 times 1 factorial, etc., k factorial, plus that k plus 1th term, k plus 1 into k plus 1 factorial. So that will be the sum of the first k terms by the hypothesis induction, k plus 1 factorial minus 1 plus k plus 1 into k plus 1 factorial. By pulling that k plus 1 factorial outside, we get it is k plus 1 factorial times k plus 2 minus 1. This k plus 1 factorial into k plus 2 can be combined as k plus 2 factorial minus 1. And that is the right-hand side of P of k plus 1. So since the left-hand side is the same as the right-hand side, the result is true. So we usually use this symbol QED, which is a Latin phrase which literally means what was to be shown. So this is what we have to show, and hence the proof of this mathematical induction method. Let's see another example. Maybe instead of using some numerical result, let us check whether the mathematical induction is true here in this case. The problem is, Suppose an ATM machine has only $2 and $5 bills. You can type in the amount you want and it will figure out how to divide things up to the proper number of 2's and 5's. The claim here is the ATM machine can generate any output amount. The machine has got only $2 bills and $5 bills. So in order to prove this, we have to have an assumption P of n. Let P of n be that the ATM machine can generate any output amount n greater than or equal to 4. Here the base case is n is equal to 4. So we have to prove that the base case n equal to 4 is true. If n is equal to 4, yes, it will be true because it can have two 2's. By taking two 2's, you know that this result is true. For the inductive step, we need a hypothesis, induction hypothesis here, and that is P of k. Let us suppose that the machine can already handle n greater than or equal to 4, and we have to prove this for P of k plus 1. So to prove for k plus $1, we are proceeding as follows. Then to prove this k plus $1, we divide this into two different cases. Say case 1, let us assume that it contains a $5. The machine contains a $5 bill. So in which case, we can replace the $5 by 3 2's. So 3 2's will be 6. So instead of $5, we can replace that $5 by 3 2's, and hence you have got k plus $1 here. Suppose if it contains only 2's, no 5 at all, then there must be at least two 2's, and we can replace those two 2's by 1 5. When you're replacing two 2's, which is we are replacing $4 to one $5, then the total comes to k plus 1. And that is the proof. So in this video, we saw how to use the mathematical induction. Mathematical induction is often used as a method of definition as well as a method of proof. So we proved for a numerical value, and also we used this mathematical explanation for an ATM machine problem. Thank you for watching this, and thank you for supporting this video. Thank you.